if we're talking about quantum numbers, let's review. First of all, how many parts to a quantum number are there? 4. There are 4 parts, right? The first part is N, then L, then M, then we just say MS for the spin states. But this first part of our number gives us the energy level. Okay, so let's just review here. You don't have to write this out necessarily, but this tells us the energy level of our electron. The second part of our quantum number, what's that tell us? We go energy level, then shape, right? It tells us the shape of our electrons. And do you remember the numerical values given to the shapes, right? It goes S, P, D, then F, right? S, P, D, then F. The next part of our quantum number doesn't tell us the shape of the orbital. It tells us the version or the orientation, right? Which version of the p orbital or of the d orbital is there? And then the last one tells us the spin state. Okay, so it's really important that we understand a quantum number is not just a single numerical value, right? It's a string of 4 numbers. It's the address of that electron. So actually, I want to wait on this C+2. I'm going to throw in a different example here first. Let's just do a neutral element again here. Let's try the quantum number for bromine. Bromine, okay? Remember, the recommendation I give for starting a quantum number is to figure out what's the electron configuration end with. And bromine's electron configuration ends with what? 4p5. And so then I draw out the orbital notation for 4p5. Right? I'm going to put in all 5 of those electrons. 1, 2, 3, 4, 5. Right? And I'm going to see which electron am I focusing on, and it's the last one that I put in right there. Okay, that's the one I'm paying attention to. So can I start part of my quantum number right now? Do I know a part of it right now? Right? And the first part of my quantum number is the energy level, which is 4. And then it's a p-shaped orbital, so that means its numerical value 1. Then the next part tells us the version of the orbital. So do you remember how we figure that out? Yep, we're going to start in the middle with a 0, and we go like a number line, +1, -1. So my electron that I'm studying falls on what version of the orbital? 0. And then I'm going to say, is it the first electron to go in or the second? Right? Is it the one that's positive or the negative one? So what would it be? The negative. So it would my final part of my quantum number would be -1/2. I don't think we've done one with a negative spin state yet, but that means we're looking at the second electron that goes in that particular orbital. Those are just numerical values that are assigned to the shape. So I gave you that little table, but S is the number 0. Yeah. P is 1, D is 2, and F is 3. Okay, so S, P, D, F. Okay. So could I ever have a quantum number that starts like this? 4, 4? No. No, because I don't have an orbital shape that's assigned the numerical value 4, right? I'm just not. It goes S, P, D, F, and that's it. Okay? So I could never have that. All right, let's go ahead and jump into the example that's listed on your slides now. And it says it's C with a +2 charge. C with a +2 charge. So first of all, tell me, what does that +2 charge do to our number of electrons? Does it add 2 or are we short 2? We're short 2, right? Because we've got 2 more positives than negatives. So if I'm talking about carbon with a +2 charge, how many electrons does that carbon have? 10. It's supposed to have 12. No, it's supposed to have 6. Oh, 6. So it would have 4. So that means its electron configuration would look like beryllium's. Does that kind of make sense, right? It's got 2 less electrons than it's supposed to have. So the electron configuration for an ion like this would be 2s2. Right? Carbon, a neutral carbon would be 2p2, but it's got 2 less electrons. So we're going to take both of those electrons out of the p orbitals, and then we're just left with 2s2. Does that kind of make sense? That the end of its electron configuration would look like that, right? The full electron configuration would be 1s2, 2s2, right? Okay, so if I'm going to draw the orbitals for this, here's my 2s orbital. I'm going to need 2 electrons in that 2s orbital. 1, 2. And so how would I start my quantum number? 2, then what? 0. And now, how many versions of an s orbital is there? Just one, right? All it gets is a 0. So the only thing an s orbital can be is 0. And then I'm going to tell, is it the first electron I was studying, or was it the second? Second, so negative 1/2. Okay. Now, we need to understand, anytime we've got a 0 there representing an s orbital, our next number will always be a 0. Right? Because there's only one version of an s orbital, right? If we had 3s, we would still only have one line. If we had 4s, we would still only have one line. Right? The s orbital can hold a maximum of 2 electrons. There's only one version of each level of s orbital.
And p can hold 4?
It can hold 6. So for p orbitals, we've got 3 different lines, right? 3p, 2p, 1, 2, 3, 4, 5, 6.
Okay, yeah.
Okay. And how many can d hold? 10, so 5 versions of it.
Yeah.
And the f orbitals can hold a total of 14, which means there's 7 versions of it. Okay? All right, what questions do we have about writing out our quantum number? Okay. Now, I want to try walking it backwards. So give me the last example on there. I think it gives us the quantum number this time.
2, 0, 0, positive.
Okay. So we're going to identify the element based on the quantum number. We're going to identify the element based on the quantum number. And when I have you do this, it will always be for a neutral element. It won't be for an ion, because it would be impossible for me to tell if it was the neutral element or if it was an ion. I wouldn't know. I'm just looking at the address for the last electron here. So 2, 0 tells me it's what type of orbital? 2s. Okay? And so I know it's going to sit on that version of the orbital. That's all I got. But it's the positive 1/2. So does that mean it's the first electron to go in or the second electron to go in? First. So that means my element I'm looking for is 2s1. So what element is that? Lithium. Okay, do we see how we can work it backward from our quantum number there? Right? Identify first the level and the shape, and then you can talk about, is it the first electron, second electron, all that kind of stuff. So let's try another one of these where it's a little bit more complex than just an s orbital. Okay? Why don't we try identifying the element from this? Okay, let's try this one. I think this one's not on your slides. I'm just putting this one up here for extra practice. So we're going to identify the element that contains this last electron. The first thing we can do is identify the level and the shape. Okay, I would agree. I think it's 3D. Right? Do we see where that's coming from? Third energy level. And then this number here is shape. So it's not S, P, it's D. Okay, so 3D orbitals look like this. 1, 2, 3, 4, 5. Okay, those are the 3D orbitals. I'm going to go ahead and label them with my number line, right? 0, 1, 2, -1, -2. Okay. Now, based on my version of my orbital, which line kind of here am I going to be focusing on? -2. That's where I know my electron's going to sit. But is it going to be the first electron to hit that line or the second? The second, because it's negative. So here's what can I do this? Just like that? No. In order for me to get a second electron here, I would have had to fill all of these with 1 before I do that one. Right? So there's my electron that I'm focusing on, which means it's 3D what? 6. Okay, so now we've got to figure out 3D6 is 1, 2, 3. So it's iron, right? The last electron in iron would have that quantum number.